To the 28 of you watching, sorry it's been a while, but now that we have the first two videos out of the way, I was debating with myself about what to do next. The other day I was feeling a little gloomy, going through an existential crisis with some self-loathing on the side, you know, the whole shebang. And as I was going through that, I felt like a hedgehog in the winter. It just felt like part of me just didn't have light anymore. Everything was dark. I felt isolated. Alone. That's right, we're talking about black holes. But in order to understand what black holes are, we must first understand another concept in physics. Chapter 2. Escape velocity. So you know how when you throw something it comes back to Earth? Pretty neat, isn't it? What you're witnessing right at that moment is a little something that goes by the name of gravity. I'm sure you've heard of it. That being said, if you throw that same thing you previously threw, but this time with more force as before, you might notice that the object goes further up with a faster speed, before falling down again. From this we can draw the conclusion that the more force you put into an object, the faster it will go and the longer it will take for it to fall down. This being said, we can see that there is a speed which you can apply to a body which will cause it to go so high that it can escape the Earth's gravitational pull. This is what we call escape velocity. It is essentially the speed which an object requires in order to escape the gravitational pull of any celestial body without any further propulsion. We can calculate escape velocity through the equation v equals the square root of 2 times g times m over r. But to understand what it actually means, we must first ask ourselves, what is a force? A force is defined as either a push or a pull, and generally, if a force is repulsive in nature, that is to say that it pushes, then it's more often than not represented as positive, and alternatively, if a force is attractive in nature, that is to say that it pulls, it's usually represented as negative. That being said, we must now turn our eyes towards gravity and how it works. It should be worth noting that gravity is not really a force, but rather just the curvature of space-time, and it is because of this curvature that objects are attracted to other, more massive objects. Essentially, if you have a ship going in a straight line, and suddenly it goes by a heavenly body, from afar you could see its path curve, but from the rocket ship, it'll still be going straight. The reason as to why you see its path curve is because the fabric of space-time, the very space and time which the rocket ship traverses, is shifted, bent around the heavenly body, and so naturally, the ship would go in a straight path relative to that curved space. Everything with mass bends space-time in some amount. So ordinary things, like whatever device you're watching this on, or yourself, have what we call a gravitational field, because by simply having mass, you curve space-time, even if ever so slightly. But the bending of the fabric of space-time is so slight that it's only really noticeable with massive objects, such as, well, the Earth, the Sun, black holes, and so on. This is why we can see and experience these objects' gravitational field, but not the one of everyday, mundane things. As John Wheeler himself put it, matter tells spacetime how to curve, and curved spacetime tells matter how to move. But that's going on a bit of a side tangent from the main topic of this video, and while I'm sure I'll get around to doing a gravity video at some point, where I focus exclusively on spacetime and its relationship with matter, right now we're doing this. So for the sake of simplicity, let's just stick with the Newtonian model and treat gravity as a force. So we can now actually focus on getting a fully working equation for escape velocity. But to do that, we must first get the variables needed for such an equation. And since we're looking for a velocity to escape a gravitational field, we must see what contributes to said field. Now remember, everything with mass has gravity, so we know that mass has to do with it. But there's still a variable we're missing, and that is none other than the distance between the object and the mass whose gravitational attraction you're trying to calculate. But instead of using a symbol like d, we actually use r, to represent not just any distance, but the radius of the larger mass. Okay, so this one is gonna need a bit of explaining. If you don't want to know why things happen and need to get straight to escape velocity because you gotta know it for school or something, then skip to this timestamp. If you're like me and want to uncover the truths of the universe, then by all means, join me as I hold your hand while explaining the reason for a symbol in an equation being an r instead of a d. But before I get into any of that, I want to give a quick disclaimer. I will be explaining using the classical Newtonian model as opposed to general relativity, because this video is already long enough as it is. But fret not, I guarantee I'll do a video on general relativity eventually. I know I'm promising a lot of videos, especially when it took me like a year to get my second video out, but just... okay? But anyway, with that out of the way, let us now see how this works. So as you know, everything with mass has gravity. This then means that every single object in the universe is pulling on everything else. We went over this. This is called the law of universal gravitation. But what you have to understand going forward is that every single particle which makes up every object in the universe has a gravity of its own. But this gravity is really only noticeable when these particles clump together, whether forming a cloud of gas or a solid object. Still with me? Cool. Now, in case you don't know, there is a concept called the center of mass. This is basically just a point in any object in which all of its mass is concentrated. That is to say that all the mass of an object adds at a point, and the center of mass is that point. And in physics, in order to show the mass of an object in a diagram, we usually just represent it as a single point in space which carries with it all the mass of an object. It is from this point that we represent the gravitational forces acting on the object. And since usually with these scenarios we almost always use spheres as our objects, we tend to represent their mass as a point in the dead center of the object. And more often than not, when expressing the gravitational force of a much larger object acting on a much smaller object, so basically just the Earth's gravity acting on an object, we also place a smaller object at the surface of the larger object, which is typically the Earth. It is then because of this reason that we represent the distance with an r instead of a d, since in this perspective, what we're essentially trying to calculate is the distance between the center of mass of the smaller object, which is very small and at the surface, and the center of mass of the larger object, or basically, the radius of the larger object. And that's why it's an r instead of a d. From this, we can then get the equation of universal gravitation. F equals g times m1 times m2 over r squared, where F is the force of attraction between two bodies, m1 is the mass of the first body, m2 is the mass of the second, r is the radius, and g is the gravitational constant. Two things are worth noting here. The first is that this equation doesn't only apply to the gravitational force between an object and the Earth. It can be applied to literally any other two objects, like the Earth and the Sun, or the Sun and any other planet, even the Earth and the nearest black hole, Gaia BH1. It's just that we usually use this equation to figure out the gravitational force between an object and the Earth. And the second thing is that we don't really know the value of the gravitational constant exactly, but we know that it's 6.6743 times 10 to the minus 11, with an uncertainty of plus minus 0.00015. Now, given as how the gravitational constant is a universal constant, that is to say that it never changes, this is way too big of an uncertainty. Because look at that. Those are the numbers displayed in full. The range which the uncertainty covers compared to the actual value is insane. But well, to be fair, measuring a number that small is... It's a pain. But anyway, despite its name, this equation is not very universal, since for one, we can't really know if it's right or wrong when gravity is very weak, since in those cases it's too weak to measure, and it outright breaks down in places where gravity is insanely strong, like in black holes. But more on that later. Anyway, we only need to cover one more thing of the law of universal gravitation in order to get back to escape velocity. As I've said before, gravity is affected by an object's mass and radius. But you might be wondering what the radius has to do with it. Shouldn't mass alone determine the gravity if everything that has mass has gravity? And well, yes, but to an extent. Remember when I said that we represent bodies in physics with a point mass? Well, you might notice that point mass has nothing to do with the radius of a body. So yes, from afar, you would feel the same gravity from two distinct heavenly bodies, provided that they both have the same mass. But remember, we're dealing with the surface of a body for the escape velocity, and that's where radius comes into play. The denser the body, or how much mass it has per unit volume, the more gravity it will feel at its surface, because you can get closer to its center of mass with all of the objects still pushing on you. Now don't be fooled. You won't experience the same gravity with the same mass and the same distance from the center of mass as the first one. This is because, if you were to be in the latter scenario, there would still be some of the particles of the larger mass behind you which exert their own gravity themselves, essentially pulling you, even if ever so slightly, away from the center of mass, so you wouldn't feel the full gravity of the object in one direction because some of it is acting on the opposite direction, and some more is acting in various other directions. But if we were to look at the former scenario, then by only being at the surface of the smaller, denser body, you experience all of its force in one direction. That's why you might hear that denser bodies have more gravity than bodies with minor density, or that a black hole has more gravity than a star with equal mass. It's not that it has more gravity, it's just that that mass which provokes gravity is much more spread out and hence much less unified. So that's why when figuring out escape velocity, we must know both the mass and the radius of the body we're escaping from, provided that we're in its surface. In short, the closer you get to a body, the more of its gravity you feel, and the denser the body, the more gravity you feel at its surface. So that's why we have to know about the radius of a body, in this case the Earth, in order to figure out the velocity an object needs to escape it, because we're escaping from the surface. The only other thing we have to worry about now is the energy required to get an object into escape velocity. In this case, we have to worry about the gravitational potential energy, basically how high an object is, or its energy due to a gravitational field, with the formula U equals minus G times M over R, where the big M is the mass of the larger body, the small m is the mass of the smaller body, and the G has a negative sign to imply that the gravitational force is attractive in nature. And we also have to worry about the kinetic energy, the energy of the motion of an object, with the formula EK equals 1/2 times m times v squared. Now remember, we want to overcome the gravitational potential energy of the body whose influence we're escaping, or taking off from. And to do that, we must then match the gravitational potential energy to the kinetic energy of the rocket as it accelerates upwards in order to find the minimum velocity it needs to escape the gravitational pull. So we can then equate the kinetic energy to the gravitational potential energy, just like so. As you can see, velocity is already a variable in our equation here, so all we have to do is rearrange for it in order to find the velocity needed to overcome the gravity of the heavenly body of your choice. Since that's the velocity needed to get enough kinetic energy to overcome the potential energy of the heavenly body. Doing so will give us this equation, which you might recall from the beginning of the video. And now that you've come all this way, you might notice that there is no small m to represent the mass of the smaller object. This means that as long as an object is going the minimum speed necessary to overcome a gravitational pull, it doesn't matter what its mass is. So a baseball going at escape velocity would be able to escape the Earth just as easily as a rocket going at escape velocity. Earth's escape velocity is around 11,186 meters per second, or 40,270 kilometers per hour, which is the minimum speed the Apollo missions had to reach in order to complete their mission, getting to the moon. So with this knowledge you have now acquired, you might now imagine that every heavenly body has an escape velocity. There's always a speed you can go at to escape any planet or any star even. I mean, that's what they do in Star Wars, and as we all know, Star Wars is very scientifically accurate.
Kinetic energy needed to move this behemoth is over 454 trillion joules. Lightsabers make no goddamn sense.
Star Wars is pretty much no respect for Albert Einstein as a general rule, so, sorry.
Your lightsaber, if it were the opposite charge, it would actually get attracted to the blade. Writers stopped giving a shit and just snorted all the coke in the room.
Okay, but for realsies, it does seem like any cosmic body has an escape velocity, right? I mean, even if the gravity is so strong that our little Arc 170 starfighter can't escape it, or any other thing with mass for that matter, then surely light can, right? Because stars glow, so they emit light, which means that not even the heaviest, densest stars can keep light from escaping because we know that photons of light are getting out of such stars, traveling across space and getting into our eyes. I mean, even neutron stars emanate light, for crying out loud. There is not a single object in the universe that has such a strong gravitational pull that not even light can escape. Oh yeah, except that. Black holes are things in the universe which are so dense that even light can escape once crossing the event horizon. That's the reason why there's a black sphere in the center, since no light in that region is able to make it out into your eyes. Properly describing black holes as I have with escape velocity thus far is really complex and will take very long, so for now, I'll do my best to simplify them in a digestible chunk because this video is already pretty lengthy, but I promise to cover them in a later video, math and everything. Probably in the video about space-time. But for now, why don't we take a look into how a black hole forms? I'll spare you most of the details of the life cycle of a star, because again, this video is already way too long. All you have to know is that stars run in a process called nuclear fusion. So basically, they have a lot of mass. This means that gravity acts on the star, trying to compress it. This then causes pressure in the inside of the star, so much that the nuclei of atoms are pushed together with such a force that they fuse together. This process releases some energy, and if we were to repeat this for the billions upon billions of atoms inside of a star, we get a lot of energy released from this nuclear fusion stuff. Enough energy to counter gravity. But the mass of the star is limited. This means that you can only have nuclear fusion happen so many times. Eventually, most, if not all, atomic nuclei inside of a star will have been fused. So we get to a point where there is no longer energy being released from nuclear fusion, which is what counters the gravity of a star. So, gravity wins. There are different kinds of stars which all lead to their fascinating little phenomena when they run out of fuel. But as for really, really massive stars, which are the ones we care about right now, well, when the time comes for gravity to win, they get compressed just like any other star. But what sets these stars apart is that they have so much mass that gravity just doesn't stop compressing them at any point. It keeps squeezing them and squeezing them and squeezing them until eventually it forms what we call a singularity, a single point in space with zero volume and infinite density. And do you remember what I said a couple minutes ago? The closer you get to a body, the more of its gravity you feel, and the denser the body, the more gravity you feel at its surface. When you have an object with zero volume but infinite density, the escape velocity you need to blast out of its gravitational field increases the closer you get to it. And with a singularity, no matter how close you get to it, you'll always feel the full force of its gravity. So the closer and closer you get to it, the more and more velocity you need to escape it. And eventually, a certain distance away from the singularity, the escape velocity is equal to the speed of light. As you might know, the speed of light is the fastest thing in the universe. And if nothing can go faster than the speed of light, the moment the escape velocity is equal to that of light, nothing can ever escape the black hole. This is called the event horizon, otherwise known as the point of no return. If its edge actually had a length, then there would be photons, the particles that make up light, perpetually swimming away from the singularity, since the escape velocity at this point is equal to the speed of light. But because the horizon has no length, the photons either narrowly escape, or they fall in. It is because of this, because light can never escape past the event horizon, that beyond this point in the black hole, we can only see a black sphere, since no light is coming out of it and into our eyes. So we don't really know for sure what's inside a black hole. Even with general relativity, our theories break down once we reach the singularity, because of the whole zero volume and infinite density thing. Some believe that the gravity is so strong that it infinitely curves space-time and as a result, opens up other parts of the universe, making a sort of wormhole. Others believe that it leads to parallel universes. Others are of the idea that black holes eventually spew out all they devour elsewhere in space-time through the hypothetical white holes. But those are all stories for another time. This is the Oxford Coffee Club, signing off.